A warm welcome for the second session on a chapter called Chemical Kinetics. I will just recollect what I taught in the last class and then I just shift on to the today's session. Hope you are trying to understand the chapter, which is very easy and concepts are friendly to you all. So this chapter, the first session which I took, I just explained what is chemical kinetics, and I said definition, and I said it's a branch of chemistry which deals with three factors: rate of reaction, mechanism, and factors affecting the rate of reaction. From there I shifted and said, what is rate of reaction? It is change in concentration of a reactant or product with respect to time. With the help of a graph I explained, and we came to find out what exactly is the unit of rate of reaction. I said rate of reaction concentration by time, that is mole per liter per second, that is mole per liter per second. From there we shifted to where exactly we can fix kinetics, because we have three different types of reactions: very instantaneous reaction and very moderate reaction and very slow reaction. We ruled out the application of kinetics in very fast and instantaneous and very slow. We want to find the rate, the time interval. So we said when we can find the rate, that is only in the moderate reaction, then we can apply that moderate reactions can come under kinetics. That is, we can find the delta T, that is T2 minus T1. From there we shifted to the types or factors affecting the rate of reaction. I said four factors which affect the rate of reaction. That one is the nature of reactant, then we discuss about the concentration, then we discuss about the temperature and the catalyst. I also took three examples, and to make you all write the expression, M1A plus M2B gives N1C plus N2D. Then I say 1 by the coefficient minus 1 by the coefficient into rate of reaction. I think I took three examples and tried to convince you all about the last class. And today's class is a journey which proceeds with the continuity of the first session. The journey is very simple. Today we are trying to find out what is a rate expression, what is a rate constant. Then how can we write the rate expression, and how can we proceed further to go to the order of reaction. From order we will try to differentiate what is molecularity and what is order, and from there we will try to learn how to find the rate expression and how to understand in the mechanism to which one will play an important role to write the rate expression. So of course today's class also hopefully you will enjoy, and I hope as you are trying to visualize or see this session, please see that you keep a notebook and note down the points or the examples. Definitely you will be happy and enjoying this session. Coming to today's session, the rate expression and rate constant. Let us consider a reaction. If I could say a general equation, A of A, B of B, C of C and D of T. When I come across this equation, I found this coefficient where A, B, C and D are the stoichiometric coefficients. We call them as stoichiometric coefficients. Of reactant and products. So A and B are the stoichiometric coefficients of A and B, that are the reactants. The C and D are the stoichiometric coefficients of product C and D, which are in capitals. Now the rate expression which we write now, which really creates a little complication for you all, I will try to convince that. We write the rate expression. If you go back to first PUC equilibrium chapter, law of mass action says rate of reaction is directly proportional to the product of molar concentration of the reactant, law of mass action. So whenever we write the rate proportional to product is multiplication, product of molar concentration of a reactant raised to the powers of their concentration. That is law of mass action. So I am going to write the rate, but you will find two terms have come. Two terms have come, x and y. So this rate what I write now, the rate is proportional to molar concentration of A to the power x and B to the power y, where we say x and y. may or may not be equal to stoichiometric coefficients A and B. According to you all, I should have written A, small a and small b, a to the power of a and b to the power of b. But I brought a new term x and y. I will convince you all why the new term has come. So, the statement said where x and y may or may not be equal to the stoichiometric coefficient. The stoichiometric coefficients are a and b. They may be equal or may not be equal. Further, we say the rate is equal to, whenever I remove the proportionality, I must retain a constant called as k. And thus k, rate is equal to k, a to the power of x and b to the power of y. Now, rate of a reactant is always minus dr by dt is equal to k, a to the power of x and b to the power of y. Remember, the above equation is called differential rate equation, and the term k here is called rate constant. Term k is called as the rate constant. So, only thing the students will find difficulty, why this new term x in the place of a and y in the place of b has come. Of course, the statement tells it may or may not be. It can be equal to stoichiometric coefficient or it cannot be equal to stoichiometric coefficient. The case is when it will not be equal to stoichiometric coefficients or when it will be equal to stoichiometric coefficients. What are the parameters that we have decided to write x in the place of a and y in the place of b? We will try to analyze that as our journey continues now. So, this is the rate expression. Remember, we brought two terms now. Remember, always when we write k, remember it is a rate constant, and rate of a reaction is always minus dr by dt. And I told you the above equation, what I have just written on the board, the above equation is called as a differential rate equation and the term k is called as a rate constant. I hope till here our understanding is going well. Now, I will define the rate law. I define the rate law, that is focused on this. Now, what does the rate law says? The rate law is the expression in which rate is given in terms of molar concentration. So, the rate law is the expression in which the reaction rate is given in terms of molar concentration. Therefore, last session I told you whenever we write in a square bracket, it defines or states that it is written in the molar concentration. Let me explain to you. The rate law is the expression in which the reaction rate is given in terms of molar concentration of a reactant, with each term raised to some power. We are raising that to some power, which with each term raised to some power, again we are coming to conclusion, which may or may not be same as the stoichiometric coefficients of reacting species in a balanced chemical equation. I will repeat again, focusing on this. This is the rate expression. Seeing this, I am trying to define rate law. Very simple. If you can understand this logic here, this expression what I have written here, then the rate law will be very easy for you. The rate law is the expression in which the reaction rate is expressed in terms of molar concentration with each term raised to some power which may or may not be equal to the stoichiometric coefficient. Again, why may or may not, I will try to conclude, and next session or the same session I will try to explain how we got that x and y. Okay. Now, remember one key word, one important note I have written. The rate law for any reaction cannot be predicted just by seeing the equation. If I see an equation, I cannot write the rate law. I must investigate the mechanism. I must investigate and find out on what basis do we write rate expression. So, don't just when you see the equation, don't write the rate expression. Definitely you will go wrong. That is not the right way of analyzing a reaction, that is rate expression. Now, rate law for any reaction cannot be predicted merely looking at a balanced chemical equation, that is theoretically. But remember the key word when you write the rate expression, but rate expression must be determined experimentally. Now, the question what you will be focusing there, how do you find experimentally? I will come to a point a little later. Let me try to give 3 examples. See, 2NO plus O2 gives 2NO2. Now, if you just see merely the equation, now see here, rate is equal to K, NO2 coefficient is there, O to the power is there. Now, we can say the 2 Here what I have written the power on NO, the new concentration here, the molar exponents here is same as the coefficient. 1 is same as the coefficient. Now may be equal to the stoichiometric coefficient. Now second example you see, CHCl3 chloroform, CHCl3 reacts with chlorine to form carbon tetrachloride NHCl. Now what is the rate expression? Rate is equal to K, CHCl3 1, okay, the coefficient is 1 here, I have written 1, but Cl2 you expect to be 1, but I have written half. The question will ask me, sir, how did you get that half? When you write rate expression, I told you may not be, may be or may not be. Now it is not equal to, so may not be. Now why it is not equal? I will try to explain it. Now CH2CO C2H5 ethyl acetate, then water, you will get acetic acid and ethanol. Now rate is equal to K. Expectation CH3CO C2H5 to the power 1. Done. Here also stoichiometric coefficient is 1, the new term is 1. But when I write water, you expect it to be 1, but we have written 0. Again the question in your mind will start, how have you written 0, sir? It should have been 1. Why have you written 0? So that is what we are trying to learn. So how do you find experimentally? Okay, this is the time. How do you find experimentally? And now the next what we are going to learn is how to write the rate expression. What are the parameters? What are the criteria? Because I told you in the note that I told you the rate of a reaction cannot be just written by merely looking into a balanced chemical equation, but focus on the experimental factor. How to find the experimental factor, how to focus, we will try to learn. So what I have just tried to explain two terms here. One is a rate expression and rate constant, and a new term x and y has come, and I told you brought new term, the rate differential rate equation, and k is the rate constant. After writing the rate expression, I defined the rate law. Rate law is very important, and then I said one important term, just don't merely see a equation and write the rate law or rate expression. It is have to be predicted experimentally. I took 3 examples. In first example, I could say it is equal to stoichiometric coefficient. Second and third example, I said it is not equal to stoichiometric coefficient. Your doubt is why it is not equal to. I will try to convince you. As we finished that rate expression, right? So we said that 8 to the power of x and b to the power of 5, molar concentration of 8 to the power of x and b to the power of 5. Now the question is, how did we come to a conclusion that x may be equal to a or y may be equal to b, or x is not equal to a and y is not equal to b, or the rate law as expression in the rate law we discussed may or may not be equal to stoichiometric coefficients. Now before I could land on that, I just finished one small order of a reaction. See what you must do, see the rate expression, just sum of the powers here, the sum of the powers, just add the powers. The sum of the powers of the concentration of the reaction in the rate law expression is called order of that chemical reaction. Now you want to find the order, check the rate expression, don't see again the equation, just see the rate expression. Then after seeing the rate expression, add the powers, x plus y, order is x plus y. We are not focusing on the equation, but we are focusing on the rate expression for that chemical reaction. For that chemical reaction, you got a rate expression, see the rate expression, add the powers, and that is going to be the order of the reaction. Order is just add the powers of the rate expression. I have 3 examples here, we just finished discussing about that. 2NO plus O2 gives 2NO2, and the rate, we found that the rate expression is equal to K into NO to the power of 2, O to the power of 1, and order is just add the powers 2 plus 1, that is equal to 3. Now to write the order, I did not focus on the equation, no, it's wrong, so don't do the mistake now. So when you want to find the order, see the rate expression, and for the rate expression, how did you got this 2 and 1, I will try to explain now after this examples. Now second example, CHCl3 Cl2 gives CCl4 plus HCl, rate is equal to K, CHCl3 to the power 1 and Cl to the power of half. Order is add the powers, 1 plus half, that is a fraction. Third example, CH3H3 CH3COC2H5 plus water, acetic acid, ethanol. Rate you focus, rate is equal to K CH3COC2H5 to the power 1 and S to the power 0. 1 plus 0 is equal to 1. So again order, don't see the equation, see the rate expression. Order again, don't see the equation, see the rate expression. Order is again, don't see the equation or chemical reaction, just see the rate expression. That's what we are trying to explain the definition. The definition says the sum of powers of the concentration of the reactant in the rate law expression is called order of that chemical reaction. That's what we are trying to come to conclusion now. How did you get X and Y? So after completing order, I want to give two ideas now, two things to understand. What type of reactions are there? Now, there are different types based on reaction rates. I told you in the first session. There are three types of reaction: very fast or instantaneous, moderate or very slow. Now second is the reaction based on the steps. Reaction based on the steps. See, always we don't get a react in only one step. We may have to continue the sequences. The first step relates to second step, the second step relates to third step. It is called sequence. Some reactions are only one step. One step is that A plus B gives C. One step. Therefore, we are going to differentiate so that we can understand how to find the rate expression and how do you get the rate exponents X and Y. Just for that, I want to give two important ideas, two important concepts. That is an elementary reaction and a complex reaction. The term elementary says the reaction taking place only in one step. Only a step, only one step, the reaction continues, only one step. That means the reaction taking place in one step is called elementary reaction. Of course, there are few reactions which are elementary. And many reactions are complex. In all what organic synthesis or preparations are going on, it is not merely one step, it is a mechanism, it is a consequence, or we call sequence of steps involved. So we call complex reaction. The sequence of elementary reaction gives the product is called complex reaction. The word sequence is very important. There is a continuity. So the continuity we go further. The sequence of elementary reaction gives the product is called as a complex reaction. So two reactions, elementary, the reaction taking place in one step is called elementary reaction, and the sequence of elementary reaction gives the product is called as the complex reaction. Now our journey goes to something called rate determining step. In a complex reaction where there are 5 steps involved, in the 5 steps involved, one step which we focus will determine the rate. That is called a rate determining step. Now how to go about this, sir? Now I will define it, then we will take an example. Now what is this rate determining step? See, the overall rate of a reaction is controlled by the slowest step. There may be 5 steps involved, 6 steps involved, 7 steps. Don't worry. In that 7 steps, one step would have taken more time to complete that particular step or a particular process in that particular step, second step or third step. So what we say here, the overall rate of a reaction is controlled by the slowest step. In a reaction is called a rate determining step, called RDS, a rate determining step. Now, decomposition of hydrogen peroxide, which is catalyzed by iodide ion in an alkaline medium. So now I will take this example and try to investigate the mechanism. In the mechanism, one step is a slow step. For that I write the rate expression, then I come to the order of the reaction. So make it more clear. So the overall reaction, in that overall reaction there may be several steps. In that one step is slow step. For the slow step we call it as rate determining step. For the rate determining step we are trying to learn the mechanism. In the mechanism it has sequence of elementary reaction. Let me give an example. Decomposition of hydrogen peroxide, which is catalyzed by iodide ion in alkaline medium. 2H2O2 I minus in alkaline mediums gives 2H2O plus O2. 2H2O plus O2. Now when I investigate, I found there are 2 steps in the reaction. 2 steps. The reaction follows 2 steps. First step, H2O2 I minus gives H2O and IO minus, slow step. Second, H2O2 plus IO minus gives H2O plus I minus plus O2. If you add both the equation, you will get back the overall reaction. Now, when I investigate the mechanism, I found the first step to be slow compared to the second step. The first step to be slow compared to the second step. Then how you can ask me, sir, how did you find slow? Now, we take the time taken to complete H2O2 to form H2O, I minus to become IO minus. Maybe if I compare 10 minutes and this is 5 minutes, 10 minutes means it has taken more time, slow step, slow process, a slow step, a slow process, the first step. How do you came to second step is fast? When I started H2O2 to IO minus, it formed H2O, I minus plus O2, maybe in the 5 minutes. So, compare the time 10 and 5, 10 is slow, it has taken more time, it has process taken very slow step, the slow step is called RDS. According to this mechanism, the first step is a slow step, it has the right to determine the rate of the reaction, of the particular reaction, rate determining step. That reaction, the first steps here, the first step is slow compared to second step. The first step controls the overall rate of reaction, that is what is called, that is called RDS, rate determining step. Therefore, rate is equal to K H2O to the power of H2O2 to the power of 1 and I minus the power of 1, order is equal to 1 plus 1, that is equal to 2, and therefore we say order of reaction can be 0, can be 1, can be 2, can be 3 or even a fraction. Many students have a confusion here, so I am trying to minimize the confusion and trying to help you to focus on the understanding part of it. So, among these two, one will be the RDS. That means all rate expression what I have written now, okay, this rate expression I have seen the mechanism. In the mechanism, that step which was slow, for that I have written the rate and for that I written the order. So, that is why we say rate expression should not be merely written by seeing a balanced chemical equation, it has to be determined experimentally. Therefore, I have taught you the example, in the example the mechanism, in the mechanism slow step, the slow step is called RDS calls rate determining step, for the rate determining step is the rate expression, for the rate expression you write the order. Therefore, this exponent x and y, I think I have convinced you all how we get x and how we get y. It is not merely seeing equation, but seeing the mechanism. Now, as we have completed the rate determining step, now just we move on to something called molecularity. Then I will differentiate what is the different order and molecularity. Okay, so the number of reacting species, atoms, ions or molecules taking part in an elementary reaction which must collide simultaneously in order to bring about a chemical reaction is called molecularity of reaction. So, the reacting species collide, when they collide they are going to form the product, and now what we are focusing on, see the reaction is a balanced chemical equation, right, it has formed the product, right. Now, you must see how many reacting species are involved, how many reacting species are involved, that means species, number of see one, only one is there. Ammonium nitrate forms nitrogen and 2H2O. It is called unimolecular. Why unimolecular? Because only one mole of the reacting species are involved. Now, if it was written 2NH4NO2, I would have written here bimolecular. Either same molecule can have 2 moles, not an issue, but together also 1 plus 1 can also be 2. Just focus on the reacting species. Now, 2HI, hydrogen iodide, gives H2 and I2. Now, how many moles of HI is there? Number of reacting species 2. That means it is called as a bimolecular reaction. Now, 2NO plus O2 gives 2NO2. It is called trimolecular. Focus on this 2 plus 1, 2 plus 1, it is 3. That is called trimolecular reaction. So, that is the logic here. The logic is 3. See, we can focus here. We can say the number of reacting species, atoms, ions are taking part in an elementary reaction. We cannot say it is a mechanism, we are not speaking on mechanism, we are speaking only about elementary step, then which must collide simultaneously and bring about a chemical reaction is called molecularity. So, you can have unimolecular, you can have bimolecular, you can have trimolecular. That is what is called as the molecularity of a reaction. That is the molecularity of a reaction. Now, we must differentiate between order and molecularity, different order and molecularity. Of sometime the examination also they have asked, write any two difference between order and molecularity. Now, order of a reaction and molecularity of a reaction has a lot of difference, which I am going to differentiate now. Now, what is order? Order is sum of powers. What is molecularity? Sum of coefficients. What is order of a reaction? Sum of powers of a concentration terms present in the rate equation is called order. So, order is sum of powers in a rate equation, in a rate expression. That is the logic here. We have discussed already a lot about this. Okay. So, sum of powers of concentration term present in a rate equation is called order. Now, remember here, it is sum of coefficient of a reactant molecule present in a chemical equation is called molecularity. So, in each equation you see the is a number of species, number of moles, number of atoms, ions or molecules, then you call it as sum, add the coefficients. Here I have written add the coefficients here, 2 plus 1, 3, 2, bimolecular, only 1, unimolecular, sum of coefficients. Now, point number 2, it is an experimental property. Why it is an experimental property? You know, we just ran through the expression that we called an example to find the RDS, and RDS rate expression order. That means order is an experimental property. It just cannot be seen one step somewhere and we cannot write just see the equation, we must see the experimental factor. Now, what is molecularity? Remember, molecularity is nothing to do with the practical concept. Only thing is that they should collide and form a product. That is the only criteria. See the equation and write the molecularity. Order can be 0 or fraction. What is molecularity? Definitely molecularity is always a natural number. Molecularity cannot be 0. At least it should be unimolecular, bimolecular, trimolecular, but order can be 0. That we will discuss it more later. How can we get a 0 order reaction? We will try to discuss that later. So, in a complex reaction, we discussed about that just now. In a complex reaction, order of overall reaction is equal to order of the slowest step. There is something called order of overall reaction is equal to order of the slowest step. Now, coming to the molecularity, the complex reaction in a we can have a complex reaction. What is the logic here? In a complex reaction, each step has its own molecularity, very important for us. Order is like one step will decide the rate, for that rate you write the order. But molecularity is like the complex reaction. I told what is a complex reaction, sum of the sequence of elementary reactions is called as a complex reaction. In a complex reaction, each step has its own molecularity. There is no something called as overall molecularity. There is no concept called overall molecularity. So, this is the main differences which we try to bring about between order and molecularity. That is, we have taken 3 examples here and a difference here. So, coming to session 2, I want to give few questions which will recreate a memory of the session what you have seen, okay, what you have heard. Hope you are writing somewhere in the paper and trying to understand the concept. Okay. So, define an order of a reaction. I have given a statement to that. I have discussed a lot about it. Define a molecularity of a reaction. I have given 3 examples: unimolecular, bimolecular, and trimolecular. What is a complex reaction? I told you sequence of elementary reactions called as a complex reaction. Of course, write any 2 difference between order and molecularity. I have given 4 differences between order and between order and molecularity. Define rate law, very important. Which we just discussed at the earlier. Then we discussed how to get the rate expression and all. So, this is the 5 question which will try to summarize what I have taught you in this session 2 of chemical kinetics. Hope you are writing there. When I am discussing in the class, you are making a note of it. Definitely you will have some doubt. Try to recollect once again as you go through the session. You will definitely understand. After that also, if you have any doubt, try to contact or try to log into the website or to the link which is given below. Definitely I will be helping you all to discuss your doubts and coming back, meeting you all or connecting back to you with the clarification of doubts. So hopefully we will meet again in session 3, and I request you all to have a continuity. Session 1, session 2 will try to link to session 3, otherwise again it is a difficult task. Okay, so try to be in connectivity with the chapter. 2 sessions are over, session 1 and session 2 connects to session 3. Hope we will meet again. Till then, take care. God bless you. Stay safe. Stay home. Thank you so much.